Looks good.
Yeah, thanks everyone. Thanks for the opportunity to present. And today I'll be talking about wildfire plume rise, especially in the recent work in constraining the vertical allocation of wildfire emissions using DIALHSRL data. So this work is funded by NASA and NOAA FIREX-AQ project, and I'd like to acknowledge my collaborators from NASA LiDAR team and the NASA Fuel to Fire team for making their data available. So why do we study the wildfire plume rise? Wildfire is basically a significant concern of the air quality and human health. So unlike the anthropogenic emissions that usually happens at the ground level, wildfire emissions can be injected into an upper level in a higher PBL and above the PBL or even in the stratosphere. So the wildfire plume rise is a very significant process that happens frequently for some large fires. It is created and induced by the convection energy and heat energy released from the burning, and also it modulated by the entrainment and detrainment process with the environment atmosphere. So as there are wind shear and the wind speed get higher and higher in the free troposphere, the plume smoke that got injected into the free troposphere can be transported to longer distance. Therefore, the plume rise determines the location of the smoke that has been put into the atmosphere, and also it determines the impact distance of the wildfire plume. So the injection height and the amount of the injections are key inputs in the air quality models, but still there are very large uncertainty in these parameters in the models. So the existing studies mostly focused on the injection height. However, we have there is a lack of knowledge in the amount of the smoke that get injected above the PBL. So here in this work, we'd like to answer the questions that how are the smoke emissions vertically allocated, and how much smoke can be injected into the free troposphere. So the data to be assimilated is collected from the DIALHSRL LiDAR system. It is an airborne LiDAR on board the NASA DC-8 aircraft. So the data is collected from the FIREX-AQ field campaign. Here I'm putting a picture of this sensor on the bottom left. So the sensor has two, basically it has two sensors, one pointing to the thinnest direction and the other one pointing to the nadir direction. So it provides the total column observation of the aerosol properties, and it provides the ozone profile, backscatter, extinction, and the depolarization. So in this talk, I will present the result for 3 fires that has been sampled and selected from the FIREX-AQ Western field campaign. The first one is the Shady Fire, which is a forest fire that happened on July 25th in 2019. The second one is Tucker Fire, which is a grass fire, so it's much smaller than the other 2. And the third one is the Williams Grass Fire. This one is the largest one that has been sampled during the FIREX-AQ campaign, and it is contributed by mixed types of the fuels of grassland and forest. So here is the data that we want to assimilate. The initial idea was to assimilate the aerosol extinction, which is also a diagnosed variable in the model system. However, due to the LiDAR sensor property and the sensor features, there are the backscatter data. So the aerosol extinction data needs a larger standoff distance from above and below the aircraft. So we see that in the first panel, we see that there is a white band of missing data, which is created by this standoff distance. And the vertical band of the missing data corresponds to the turning of the aircraft. Therefore, we use another option. So we derived the aerosol extinction coefficient based on the backscatter coefficient. So it is derived by using a constant LiDAR ratio, which is the ratio between the extinction and backscatter. So a constant LiDAR ratio is defined is extracted from LiDAR data for each segment of the LiDAR profiles between each 2 flight terms. So the bottom panel shows the derived aerosol extinction, which from the backscatter coefficient, which shows a great consistency with the aerosol extinction measured by the LiDAR. So the inverse modeling system is shown by this flow chart. The key forward model is WolfAM, which is based on the WolfCam version 3.6.1, configured with a simplified aerosol-aware macrophysics scheme. So this one runs faster than the typical full chemistry version and saves computation time, and it has been applied to several field campaigns. For the biomass burning emissions, we use the QFAD version 2.5, and it is remapped diagonally and it's spatially based on the fuel to fire data. Fuel to fire is a bottom-up inventory of the fire emissions during this campaign. So we derive the CO tracer emissions from the biomass burning emissions and use this to drive the WolfAM model to get the Jacobi matrix and calculate the cost function, and the optimized smoke emissions are derived by minimizing the cost functions. For comparison, the inversion results are also compared with the default Plume rise parameterization in WolfCam, which is based on the Freitas scheme based on these two papers. So here is a further look at the construction of the Jacobi matrix. To construct this, we explicitly simulated the contribution of tracers from different time and different levels. So this is an example of schematic plot of how we constructed the layers. On the left, so we selected the bottom 32 layers from the model, and these layers extend about from about the surface to about 8.5 kilometers. To save some computation resources, we just regrouped these levels into 3 groups and use into 13 groups and use 13 tracers to track the CO emitted from each level of these grouped layers. So so there are 142 CO tracers in the total are used. These are tagged to the emissions from 13 layers per hour and times 11 hours of the period of interest. So and then another important parameter is the conversion factor. So it is used to convert the CO tracer sensitivity to the aerosol extinction values. So this conversion factor is derived from 2 simulations. The first one is the simulation with the fire emissions turned on, and the other one is with only the anthropogenic emissions, and the fire emissions are turned off. So the difference between these 2 simulations would contribute to the calculate of the alpha, of the conversion factor alpha. So here, these 2 plots shows how do we distribute the tracer emissions. So the hourly emissions follows the QFAD data and remapped following the fuel to fire bottom-up inventory to represent the diurnal cycle. And then for the tracer emissions, in the 11 hours period of interest, the tracer emissions are distributed vertically and evenly at each level. So the strength at each level of the emissions for each level is consistent. And for the times out of the period of interest, we use the emission profiles from the default Plume rise scheme. So after using the inversions, we have firstly tested the simulation, use all the individual LiDAR profiles. So we found that there is a problem in this case because when the plume is shifted between the modeled plume and the observed plume, there would be some issue. For example, in these 2 panels, I'm showing the observed aerosol extinction enhancement and the constrained results. So although the aerosol extinction above the PBL height can be constrained pretty well, the plume below the PBL is still underestimated after the inversion. This is because that there is some offset in the location of displacement of the simulated plume compared to the observation. So the inversion would try to constrain the places where the plume are not observed. So again, this would create the underestimation. And the spatial plot confirms this case. So the spatial plot here is showing the AOD calculated below the PBL height. We can see that the observed location of the plume, which is represented by the colored dots here, is a little bit shifted to the north compared to the simulated plume, which is denoted by this, showed by this color shading. So this is the problem of assimilating all the individual LiDAR profiles. To overcome this difficulty, we choose to assimilate the transect accumulated aerosol extinction. So for each transect collected between the flight turns and plus the plume, we just integrated all the aerosol extinction enhancements for each level, and then assimilated the accumulated aerosol extinction. In this case, we can see the improvement for the last panel. This is assimilating the integrated aerosol extinction. We can see that the aerosol loading within the PBL are better constrained. So this is the method we'll be using. And after the inversion, we are going to constrain the vertical distribution of the emissions. Firstly, let's take a look at the default setting of the default result of the WolfCam model. So these three panels shows the default distribution of the WolfCam model. This is derived from the FIREX plume light scheme. So at the default scheme, the scheme would put 50% of the column total emissions at the surface level, at the lowest model level, and redistribute the other 50% to the higher levels. And the limit of the upper and the lower limit of the injection is derived from online coupled one-dimensional model in this plume light scheme, using different convection energy that are assigned for different fuel types. So after the inversion, we can see that the constrained vertical emission distributions are showing that the first the emissions at the lowest model layer are much lower than the default, and also the amount of injected emissions are higher than the default setup. So it has created a better agreement with the observed LiDAR extinction. So here, based on the constrained emissions, I'm showing the fraction of the smoke that are injected above the PBL. And in each panel of the lower row, the yellow line is the default FIREX scheme, and the blue line is the first guess of the inversion, and the red line is the analysis or the constraint result. We can see that for all of the three cases, after the inversion, the injected fraction of the emission get much higher than the default values, which means that the default setup of the FIREX scheme would be unrealistic for most cases that shows injected plume above the PBL. So another question we want to explore is that what factors are determining the fraction of smoke that are injected above the PBL? So on the left side, I show a summary of the box whisker plot showing the distribution of the hourly injection fraction for the constraint result and the FIREX result. So again, we can see that for the shady fire and Tucker fire, the fraction is about lower than 90%, and for the Williams-Fast fire, the constraint injection fraction is much higher, and it can reach nearly 90%. Firstly, we examined the basic features of the fires. These are the fire radiative power, total carbon emissions, and the injection height. We can see that these three has a pretty good correlation, which shows the feature of the total energy or the total emissions for each fire. And this makes sense because the injection height and emission would correlate with the fire radiative energy, which is determined by the amount of the fuel that it can provide during the burning. And but however, the FRP, total carbon emissions, and the injection height do not show much correlation with the fraction of injection. So we also examine the environment variables such as the PBL height and the Richardson number. So we can see that the Richardson number shows some relationship with the fraction of injection, as the Williams specifier is showing the largest value of fraction injection. It can be explained by the strongly negative Richardson number, which indicates the very unstable stratification for this case. However, the Shady and Tucker show very similar fraction of injection, and the Richardson number are also less negative compared to the Williams specifier. And also PBL height are showing some relationship with the fraction of injection, as the Williams specifier showing a higher fraction of injection. It is related to the moderate PBL height, because this means that the fire energy is enough to penetrate the PBL in this case. So and still there are not very clear correlation between these parameters, which means that there is not solely a single variable that is dominating the fraction of injection, which means that the fire energy and the environment conditions are contributing to the injection fraction simultaneously. And this needs some further investigation. So in summary, this investigation focused on the inversion of the emission allocation. So this inversion framework has provided promising performance in constraining the vertical distribution of the smoke emissions. The constrained proportion of the smoke emissions are much higher than the default scheme in the WolfCam model, which is to be considered in the future development of the wildfire modeling. So thank you for your attention.
Thank you for a great talk. I have a question. So you say you looked at different PBL parameterization, or have you looked at if you use a different parameterization in WRF, what would be the
So in these tests, we use the same PBL parameterization, and I agree that different parameterizations could provide different result of the injection levels, because the different parameterizations would provide different temperature profiles and PBL height, which will affect the performance of the Plume ride scheme and the environment. Yeah.
And did you run data simulation with WRF?
So this one is it's done offline. So this is not achieved by the assimilation in WolfCam. We constructed this inversion offline, and derive the emissions and the tracer concentrations separately. Yeah.
Thank you. That's good talk. I'll pass it on to Xinxin for the conclusions.